Okay, so there we go. We should all sort of see now at the top that we're recording. So again, reminder, please do not stop the recording. You do have the power to do that, so please do not do that. Okay, so today we're just going to pick up where we sort of left off with classical lamination theory. I'm going to do another just really brief, quick review on things that we should have covered in 429, and then I'll sort of pick up with the new material using the whiteboard pad. All right, so here we go. I'm going to share my screen, and you should all be able to now see my screen here. I'm going to pull up the notes from classical lamination theory. And here we are. Okay. So we went through the whole rigmarole last time about reviewing some of the material from 429. I just want to emphasize again the classical lamination theory concepts that we had from 429. So again, let's review some of the basic ideas about lamination theory. So we're stacking multiple lamina on top of each other to create a laminate. Okay, so there's a difference between that word lamina, which is one single layer, and a laminate, which is a stack of layers. So here we can arrange them in a variety of ways, and we denote the laminate stacking sequence using a series of angles, where the angles are the relation between the directions of the fibers in the unidirectional layers relative to some global coordinate system. So if we have a unidirectional laminate, we have many layers of 0-degree lamina, or we can have a quasi-isotropic laminate, where the stacking sequence varies something like 0, 90, 45, minus 45, so on and so forth. Okay, and then we have these definitions for the various lamina in the laminate. So the total height of the laminate stack we're calling H, and we place the coordinate system when we're talking about laminates generally at the center of the laminate's midplane. Okay, so here we have our coordinate system XYZ at the center of the stack of the lamina that create the laminate, and the location of each individual lamina in the laminate are described by the variable z. So the bottom of the lamina is zk minus 1, and the top of the lamina is zk. So we're just denoting where that lamina is located in sort of a z variable space using that particular variable z. Okay, so this allows us to define where our lamina are in our laminate stack. Now we want to relate strains to stresses in the laminate stack. And we made an assumption that if we load a particular laminate, that the strain would be continuous through the laminate. And that sort of makes sense, because if you have discontinuous strain, that means you have a discontinuity or a hole inside of your piece. So we're going to assume that our material is continuous throughout and we don't have any discontinuities in the strain distribution. So we can employ sort of a longitudinal strain, which is like a tension or a compression. And we can also induce bending strains, which might lead to a linear distribution of strain through the piece. So you might end up with a strain variation in, let's say, the X direction through our laminate with what you see here, sort of this general idea here, where we have a combination of both bending, which would create this linear distribution, and also some tensile force, which creates an additional tensile load generally on the piece. Now we know that the stiffnesses of each of the individual lamina are not the same, because we have fibers running in different directions in the different lamina. And so we might have some relative stiffness of each lamina that varies through the thickness, and that causes a variation in the stress through, if you want to just think of a one-dimensional Hooke's law as strain times modulus equals stress, we got a stress variation that looks like this and is relatively discontinuous. So at the end of the 429 class, we went through a whole derivation to sort of show the relationship between the strain we might apply through either bending or longitudinal straining relative to the stress that is created. And that equation looks something like this. A little bit tedious and cumbersome, but it's a matrix equation where we have here the stresses on the individual lamina of the kth layer, sort of on the left-hand side of this equation here. Sigma x, sigma y, and tau xy of layer k is equal to the stiffness matrix of that particular lamina in the orientation that it has, multiplied by the midplane strains in the laminate, that's this particular vector here. So this is the strain in X, maybe the strain in Y, and also the shear strain, gamma XY, plus Z. This is the location of lamina K, multiplied again by that stiffness matrix, multiplied by the curvature of the laminate. And so the curvature is how much the lamina or laminate is curving in space. So if longitudinal strain epsilon is how much it extends or compresses, this kappa value, this is the variable that we're using here for curvature, is how much the lamina is curved due to the bending that might be applied. Okay, so in shorthand, we write something like this, where we're representing 1x3 vectors and 3x3 matrices appropriately. Okay, so here we have the stresses in lamina K equal to the stiffness of that particular lamina multiplied by the strain in that lamina, the longitudinal strain, plus the location of that lamina in space multiplied by the stiffness, again, of that lamina K, multiplied by the curvature that is induced that we enforce in our particular lamina. Okay, so this is where I'm going to sort of end what is the review from 429. And now we'll move on with what I think is sort of quote unquote new material. All right, so I updated the lecture notes to include the slides here. I think Anson made a mention on Monday that the slides that were up on Blackboard were not current, so I updated the slides and you should have them available. And I'm going to start my material on this particular slide here. So I'm going to move to the whiteboard now. I don't know if I want to call this a whiteboard, my electronic writing pad, and begin discussing some of the laminate theory in a little bit more detail, relating the forces that we may apply to the laminate to stresses and strains that develop. Okay, so I'm going to stop sharing the PowerPoint slides, and I'm going to now move to share the writing pad. So we should all see the writing pad here now. And again, one more time, I'm just going to solicit some comments maybe here. How's the microphone sounding? Are you guys awake? Do you need more jokes? Do you need more coffee? I need some coffee. Let's do this. It's early. Is there anybody like on the West Coast, like California, that got up at 6 a.m. California time for this? I'm just curious. I think Will Borup is in Colorado. More jokes, says Matt. Yeah, Will's in Colorado. Yeah, I didn't know if you had gone home or not, Will, but 7 there. Good job, man. Props to you. Are you like laying in bed right now or what? I would be if I were you. Okay, so we'll move on and I'll start working on the whiteboard here. Okay, so again, if you have questions during lecture, put them in the chat and I'll try to answer them as we go. Okay, so we want to relate, we have a relationship here now between stress and strains and curvatures. Okay, now we need to talk about how those strains and those stresses developed originally and the relationship between what forces and moments we might put onto our laminate and the stresses that develop. Okay, so see if this is working. Of course it's not. Yay technology. So now we need a relationship between applied forces and moments to stresses and strains. So we have this relationship between stress and strain, which I just kind of showed in the PowerPoint presentation. But now we need to know how the forces that we might apply to our laminate create those stresses and strains. Okay. So let's consider a laminate with following geometry. Okay. So we have some laminate here, and I'm just going to define some geometric parameters of this lamina. Okay, so here we have our laminate stack. I'm going to do my best again to draw. I think I'm getting a little bit better, but still a little suspicious. All right, we have our coordinate system coming off of this, which is x, y, and z. And so when I go through the next sort of derivation for this particular class, we're going to define some geometric parameters of this particular laminate, and namely that we have sort of dimensions of this laminate, which would be here, let's call this the length in the y direction of this particular laminate. We'll call this the length in the x. And also generally the thickness of this particular laminate. Let's call this T. All right. So the bottom of the laminate stack would be at location negative T on 2, and the top of the laminate stack would be at location positive T on 2. All right. One other sort of parameters that we need to define is we need to talk about the cross-sectional areas on this piece. If we're going to relate things like forces to stresses, then we have to define some cross-sectional area upon which we are acting. So here, the cross-sectional area for this particular face, I'm just going to call AY. This is the area that is on the projection of the y-axis. And here, this is the area AX, which is the area on the face where the x-axis is relatively protruding. Okay, so these are some of the geometric parameters that we're going to use in the upcoming derivation, and we'll come back and sort of draw the forces and sorts of things on this picture a little bit later. Okay, so we need to relate forces and moments to stresses. Okay, so the way we're going to do that is we're going to assume that we know what the stress distribution is. So remember, our stress distribution was different for each particular layer based on the strain that we had. So here we will assume we know things like sigma x, sigma y, and tau xy. And with that idea in mind, then the force that is acting to create those particular stresses is simply the integral of the stress over the area on which they act. Okay? So if so, then the force that was used to create that stress, let's talk about just one general direction here, Fx, is the integral of the stress over the area in which it acts. So here, this is the integral on AX, right? That's the area on the sort of X face of the stress in the X direction on that area dAX. All right, so this is integrating that stress distribution over the area, okay? Now we can expand this. This is an areal integral, so this is a double integral. So let's expand our double integral here. And we can write this as the integral from 0 to Ly. Remember, if I page up here for just a second. Remember that Ly here is this length of this particular piece in this direction. Okay, so I'm integrating from 0 to Ly across y. And then I'm integrating from negative T on 2 to T on 2. My stress distribution sigma x here, dz, dy. All right. All right. So this is the force that we're generating. It's just the integral of the stress distribution on the face. All right, so note here that by assumption, our stress distribution on X does not vary with Y. So what I mean by that, if I page back up here, is that as I move in the Y direction on this face, that's this direction, my stress in X, which is sort of the stress coming off this direction, is not changing. Okay, it's consistent across that variable Y. So it does not vary as a function of Y. Okay, so then we can simplify my fx to the following. Here we have this integral here. And again, we said this is not a function of y. So since sigma x is not a function of y, we can pull out or sort of assume that when we're integrating from 0 to ly, there's no change in this integral because there's no functional dependence of sigma x on y. Okay, so by first fundamental theorem of calculus, if this is not a function of that thing, then it just pulls out. Okay, so here this fx then just becomes ly as we pull it out of the integral, multiplied by this integral negative t on 2 to t on 2 of sigma x dz. Okay, so we have this constant here now, which is ly. That's the length of the laminate in the y direction, which is just sort of hanging out after we've gone through sort of this derivation. So let's normalize fx by ly, the length in the y direction. This gives us a force per length. What results is a new variable, which we define as nx, which is the force x normalized by the distance in y, ly, which here is simply the integral from negative t on 2 to t on 2 of sigma x dz. All right, now let's talk about what this is. All right, I'm going to come back into Teams really quick. Any questions? Any questions? Yeah, says Will. Okay, no questions. All right, so I'm going to come back to the PowerPoint slides here for just a second. Okay, so when we're talking about what this integral generally is, we're talking about nx is the normalized force in the x direction, which is this general integral from negative t on 2 to t on 2 of the stress distribution in x. Well, if we go back to what our stress distribution might look like, again, reminder that's over here on the far right-hand side is sort of the idealized stress distribution. The integral from negative t on 2 to t on 2 is just the area prescribed by the hashed out portion of this particular distribution. Okay, so nx is simply the area of this particular stress distribution. And we're assuming that this stress variation, as we're looking at the side of the laminate, is continuous into the plane of the board throughout the entire thickness of the laminate. Okay, so here we're defining nx, which is a force per unit length across the laminate, equal to the integral of the stress distribution through the thickness of the laminate. Okay. All right. Back to the pad. All right, so we can have similar derivations for the force per unit length in Y and the force per unit length of shear. And so I'll explain what that is in just a second. Let me get back to my pad over here. So similarly, we have what is Ny, which is the force in Y normalized by the length of the laminate in X. That is the integral from negative T to T on 2 of sigma Y dz. And also we have the shear force per unit length. I'll kind of show what that is in just a second here. Similarly equal to negative T on 2 to T on 2 of tau x y dz. Okay, this is the shear in each particular lamina as a function of the thickness of the piece. All right, so let's go back to what would be our drawing. I'll sort of keep the notes here as best I can. Hopefully you guys can still sort of see that. Let's go back to the drawing and maybe show what that actually sort of looks like. So here's our very crude picture of our laminate, X, Y, Z. And so let's draw each one of these things. So we have the force per unit length in X here is Nx, right? The force per unit length in Y is Ny, typically represented like this. But really what Nx is sort of this line force across the piece, and what Ny really is sort of this line load across the Y face of this particular piece. But typically in images, you'll see it represented in this way. So Nx, Ny, this is the normalized force per unit length in the various directions. But Ns is a little trickier, and it's actually the force that's acting across the face in either one of these directions in shear. Okay, so here this is Ns, and this is also Ns. Remember by conservation of angular momentum that Ns has to balance out sort of as shear on this particular side of the laminate. And since we're normalizing by the length of the laminate in the various directions, what this actually is a force per unit length coming across the face. So what you really want to think about is a series of forces sort of acting across the face in this general manner. Okay, but more often than not, it's just represented as one particular arrow. Okay, so we're normalizing whatever force is acting in shear across the face by either the length in X or the length in Y. Okay, they should be approximately equal. Okay, so that's the forces. The moments have a similar derivation. So the moment / stress relationship is similar. And I'm just going to write that here without sort of the same level of derivation or the same depth, in that you might have something like mx, which is the moment in x, is the integral from negative t on 2 to t on 2. Now we have to include the variable z because our moment varies with the thickness z times the stress distribution sigma x dz. Okay, this here is the normalized moment per unit length in x. Okay, if you wanted to draw that on our particular laminate, that might look something like this. Here's mx, sort of, if we thought of my business card here as sort of our laminate, then the moment in x might be sort of this like bending moment that we apply to this particular laminate, okay, in that x direction. We similarly might have Oh boy, not red. My negative T on 2 to T on 2, Z sigma Y dz. All right, so this is the moments that are acting sort of on the Y direction. So if we page this thing up, I don't understand like the paging on this particular guy. But all right, so this is your MX. You might also have here your MY. So this is sort of, if this is MX, then MY is this, right? And then finally, you could have a shear moment that is applied, MS, which this one's a little bit strange, but negative T on 2 to T on 2. This one's a little bit more difficult to visualize. Z times tau xy dz. So this is the normalized moment per unit length of shear on the laminate. And basically what that basically is the torque that's acting on our piece. So a little bit difficult to draw the torque, but the basic idea here is that we might have some axis that runs through our piece. Okay, and my MS is here. The torsion that's sort of acting on this guy. Okay, so that would be sort of this kind of motion that's acting on my piece. All right. So this is how we're relating loads, NX, and moments, MX, to stresses inside of our piece. All right. So relates M and N, which is the moment and the force, to sigma xy. So this is tau x, tau xy, sigma x, and sigma y. All right. So can write in shorthand form. I'll say shorthand matrix form. So again, we're relating the loads that we apply on the piece, both the axial loading, sort of this NX and Y, and the moments that we apply, MX, MY, to the stresses that are developed. And we can sort of write this in sort of a matrix form as for axial loads, we have the following: NX, NY, and NS. This is the shear force acting across the face. NS. Here, this is equal to the integral from negative T on 2 to T on 2 of the matrix, which would be sigma x, sigma y, tau xy, dz. All right, so this is relating axial loads to stresses which are developed in the piece. And for moments, similarly, we have mx, my, and ms, sort of the shear moment, which is a little bit difficult to understand. Is the integral from negative T on 2 to T on 2 of the vector of stresses, sigma x, sigma y, tau xy, all integrated over the thickness dz. All right. So this is how we're relating loads that we might apply to the piece to the stresses which develop inside of the structure. Ooh, coffee. Okay. Now, we kind of showed what these stress distributions might look like, right? So back in the PowerPoint, we saw the stress distributions were changing as we go through the individual layers. And so we might want to discretize the integral that we've written here for the individual layers that we have. So we can take the integral that we have written here, which is the integration of the stress distribution through the thickness of the laminate, and actually discretize it to look at the summation of the integrals of each one of those individual stress distributions in each one of the individual layers. Okay, so let's do that. So now we will discretize integral to sum contributions from each layer. So what I mean by that is, if I know the stiffness of layer K, and I know the general strain distribution on the laminate, then I know the stress distribution in layer K. That stress distribution in layer K might be completely different than the stress distribution in layer K plus 1. So we may want to take the integral that we've written here and chop it up and sum the integral as the individual integrals of each one of the individual layers. That's what I mean by discretize. And so we can discretize these particular integrals by writing them as the summations of the integrals of each of the individual layers. Okay, so we discretize this here, and now we write something like the force per unit length in X, the force per unit length in Y, and the force per unit length of shear equal to, now we're going to sum from K equals 1, the first layer, to N, which is however many layers we have in our laminate. We're going to sum the integral of the stress distribution in each particular layer. Okay, so we're integrating from the bottom of layer K, which here, using our geometric description, is the location ZK minus 1, to the top of the individual lamina K, which is by our geometry ZK. Our stress vector, sigma X, sigma Y, tau xy, depending on which force that we're looking at, integrated over dz. Okay, so here now, let me make this equal sign a little bit more clear. And we're going to want to give this guy a box. He's box worthy. Okay, so again, this is the force on laminate. And that's normalized by the various lengths in the laminate. Here, this integral is summing over all lamina. And here, this is the stress distribution. In lamina K. Okay, so we're basically summing up all the stress distributions in each of the individual lamina to get us back to whatever force we originally applied on the piece. Okay, so we're relating, again, forces to stresses by looking at the stress distributions in each one of the individual layers. All right, so that's discretizing the axial loads. We can also now discretize the moment loads that are applied as well. So let's do that. So we can also discretize the moments and write something like the moment in X, moment in Y, moment in S equals our summation again from K equals 1 to N, where this is summing over all of the lamina that we have in our laminate stack. The integrals of the distributions of stress within their own respective layers. So we're integrating from location ZK minus 1, which is the bottom of lamina K, to the top of lamina K, which is ZK. The stress vector, sigma X, sigma Y, tau xy, dz. And we can't forget about our thickness here that hangs out as well, because we're now discretizing the moments. All right, so here's our discretization of the moments, which relates the moments that we applied on the laminate to the stresses that are developed in the laminate. Okay, So it relates applied moments to stresses. All right. How are we doing out there in Math Magic Land? Kind of some intense math we're going through here. We got summations, we got integrals, we got matrices, we got vectors. Anybody scared yet? Don't be scared. You can do it. I love derivations and vectors, says Justin Selesky. Well, I'm glad that you're even still awake. Okay. So that's a good thing. I need my coffee, or I'm gonna not off here. Okay, great. So no questions. I'm going to continue then. So we've only really gotten started with the complication, and that's because sort of at the beginning of this lecture, we can expand the stresses to be written in terms of the strains. So remember at the beginning of this lecture, I talked about we wanted to relate the forces and moments that were applied to the laminate, not only to the stresses, which we have just done here, but also to the strains which developed, okay? The reason that we want to do that is because we can write the stresses in terms of the material properties that we know, the stiffness matrices, for instance, and the applied strains. So we can bring in additional information because we know things like what is the stiffness of layer K. Okay, so with that information, we can make additional reductions in the things that we know and understand to further relate stresses and strains to loads that we've applied. So we can expand the stresses to be written in terms of the strains. So if we recall, Central Park and fall. No, I'm just kidding. You don't want to go to Central Park right now, promise. Okay, recall relation between stress and strain. We wrote at the beginning of this lecture, or sort of we reviewed, that the stress in lamina K was equal to Q bar, which is the stiffness in XY of lamina K, multiplied by the midplane strains plus the thickness times the stiffness in the XY direction of layer K, multiplied by the curvatures XY. So this is our relationship between the stress in layer K and the general strain inside of the laminate. So this is something that I discussed back on slide 10, I think it was. All right. So what we can do is we can take the relationship that we have here with, let's say, the loads that we applied. So this guy, the relationship between the loads we applied, whoa, baby. The relationship between the loads we applied here, and X and Y and S, and the stresses that developed, and actually substitute the general equation for stresses into this particular portion of the integral. Okay? So we're going to substitute in two equations for N and M. All right? Okay. So what results is, man, complicated. All right? I will write the resultant for NX and MX now. It will be the only time that I write something this long. Hopefully it doesn't take me the rest of the lecture time. All right, but if you weren't scared before, you're about to be scared. So that results in, for axial loads, the following. Here we have NX, NY, NS equal to, again, we're summing from K equals 1 to N, our integral of the stress vectors. But here now we're substituting the stress vector sigma xy tau xy for the expression that contains the strains that we know. Okay, so in full-blown glorious form, it looks something like this. Q11 bar, Q12 bar, Q16 bar, Q12 bar, Q bar 22, Q bar 26, Q bar 16, Q bar 26, and Q bar 66. This is my Q matrix multiplied by the strain vectors, epsilon x naught, epsilon y naught, and gamma x y naught. This is the mid-plane curvatures multiplied by the integral, which is zk minus 1 to zk of dz. All right. So this is the first portion. This is going to be plus, we're still in the parentheses here, the contributions coming from the curvatures, which is Q bar 11, Q bar 12, Q bar 16, Q bar 12, Q bar 22, Q bar 26, Q bar 16, Q bar 26, and Q bar 66, multiplied by the curvatures that I created. Is kappa x, kappa y, kappa xy. These are the curvatures on the laminate, multiplied by the integral from zk minus 1 to zk of, here now the z is included from the moments dz. All right, so what we've done is taken, I'll come back to that equation in a second, sorry if you were sort of writing it down. We've taken this equation here, which relates the applied loads to the stresses, and utilized the substitution of this equation into that expression to give us this sort of full-blown equation relating the applied loads, Nx, Ny, and Ns, to the strains and curvatures that are developed in the laminate, given the individual stiffnesses of the individual layers. Okay? So this is relating applied axial loads to individual lamina stiffness, which you all know how to calculate, and global laminate midplane strains and curvatures. All right. So a little bit cleaner form. I'm just going to share here my PowerPoint for a second, just because, in my opinion, seeing it on PowerPoint is a little more clear. All right. So I had just written on my notepad and not such great handwriting this particular expression, which is relating the loads that we applied on the laminate to the strains that develop and the curvatures that develop through the individual layers of the stiffnesses by substituting this general expression. All right, so we've done this for, here's the axial loading, and here is the relationship between the moments and the curvatures and strains that develop. Okay, so this is where we'll stop for today. We'll pick it up and discuss next time how we can relate these applied loads and applied moments to stresses and strains to actually develop things like what is the stiffness of the laminate as a whole. Okay, so that's it for material. I do want to kind of solicit the audience one more time. Just ask how generally it went. Can you hear me better? Was there issues when I turned my head towards the whiteboard to write? All those sorts of things. So Max has a question here. I understand kappa represents the curvature of the laminate, but how would you actually come up with a value for it? It looks like it should have the units 1 on length. All right, so everything sounds good this time around, better audio this time around. I just want to address Max's question very quickly. So we'll have like a little aside here. I'll share my whiteboard here with you. Got to remember to do that, screen number 2. So here we have a little aside for Max. So if we put a bending moment on a lamina or some strain that would cause it to bend, which we know occurs with orthotropic materials, you'll have a laminate that may look like this. If you have, let's say, a coordinate system that is x, z. All right, so here is our curved laminate. This is obviously like kind of a gross representation of what it is. But here, this laminate has curvature, and you can assume that the curvature it takes on is sort of the arc length of what would be a circle. Okay, so maybe that points back to some location up here. And this has a certain radius to it. Typically, we would denote the radius of this curvature as rho. That is the Greek letter rho. So then, kappa, this curvature, is 1 on rho. Okay? How's that, Max? Did that answer your question? Okay. He says, yup. All right. So again, give this video a little bit of time to render. It should be on YouTube later today. The rendering actually took faster than I thought it was going to, so it should be up by the end of the day. I'll stick around again for a couple minutes, and then I'll head over to my office hours. If anybody wants to join me there and ask questions about homework or whatever the case may be, I'll be there. Thanks for coming, and if anything, I'll see you on Friday. Oh, Hanson found an error in the notes. Okay, that is on what, slide 12? Yeah, slide 12. Oh, I see it. Okay, yeah, I'll update. Thanks for the catch there. Okay, bye.